In this video, we're going to look at the connection between free energy and equilibrium. So, in the first part of the problem, we're told that the equilibrium constant for this reaction is 5.6 times 10 to the 8th. And we want to know what is delta G naught at this temperature. So the relationship between equilibrium constants and delta G naughts are the following. All right, so we know K. All we need to do is plug in R and T. The only thing we have to do is be careful of our units. So they gave us the temperature in degrees Celsius, but we need the temperature to be in Kelvin. So the temperature will be 25 plus 273, so that'll be 298 Kelvin. And then we need to be sure, or be careful of the units on R. So I usually like to report delta G naughts in kilojoules per mole. So that means I need to use R as 8.315 times 10 to the minus 3 kilojoules per mole dot Kelvin. If I use just 8.315, that's fine, but I have to be aware that my delta G naught is going to come out in joules. So if I plug my numbers in, and my delta G naught will come out to be negative 49.9 kilojoules per mole. And if I want to kind of look at how the units came out, the way I got kilojoules per mole, right, I have R is kilojoules per mole times Kelvin, and then I multiplied that by the temperature in Kelvin, so the Kelvins will cancel, and that's what leaves me with the kilojoules per mole. All right, let's look at another example related to this same problem. All right, so same problem, but now they want to know what is delta G if I mix the reactants and products with the given concentrations. So remember that delta G naught is the value when I have everything in their standard states. So that would mean if I'm dealing with gases, everything was at one pressure, or if I'm dealing with aqueous species, as I am in this problem, then they're all going to be 1 molar. And so now, when they're not all 1 molar, that's when I have delta G. But the relationship between delta G and delta G naught is very simple. Where Q is the reaction quotient back from when we were doing equilibrium problems. So all I need to do is calculate Q. So Q is going to be the concentration of the nickel ammonia complex over the concentrations of the reactants. And of course NH3 will be to the 6th power because of the coefficient in a balanced chemical reaction. So when I calculate Q, I'm going to have and so Q comes out to be 6.4 times 10 to the 14. So now I can plug in my values in my first equation. So delta G naught from part A is negative 49.9 plus R and T and the natural log of 6.4 times 10 to the 14. So delta G comes out to be positive 34.6 kilojoules per mole. All right, let's look at a couple other questions that we can ask related to this problem. So they want to know if this reaction is product favored or reactant favored. So to answer that, whether it's product favored or reactant favored, I need to look at delta G naught. And when delta G naught is less than 0, then I know that it's product favored. If delta G naught had been positive, then that would have told me that it's reactant favored. Also, I could have used the equilibrium constant because K is bigger than 1. That's also telling me that it's product favored. All right, another question that we could ask is, given the concentrations of product reactants in part B, in which direction will the reaction proceed to get to equilibrium? If I want to use delta G for that, I'm going to use delta G as opposed to delta G naught. And so due to the fact that delta G is positive, that tells me that the reaction will go to the left. Or an alternate way to answer this question is, if I want to know reaction direction, I can compare Q to K. So here's K. If you remember from part B, we calculated that Q was 6.4 times 10 to the 14th. So also, because Q is greater than K, that'll tell me that the reaction is going to go to the left. So there are two ways that we can answer this. I can answer it with delta G, because that's positive, that tells me the reaction goes to the left, or I also know that because Q is larger than K, that also tells me the reaction goes to the left.